Right, so eBay, a really easy way to spend money that you weren't planning on spending. Let's have a look what's in the box. Lots of little boxes, 59 of them. Don't know what I'm going to do with 59 of these, but what we've got is some LED modules. Right, so what we've got here is an LED module. It's made by the company Dial Light Lumidrives, and I was just perusing eBay looking for some LED modules because I've got a few lighting projects going on in the house, which I'm going to cover in some videos shortly. And I wasn't actually looking for RGB modules, but while browsing around looking for Lumi LED's products, so things that use Luxian Rebels or Luxian Z or whatever, those kind of LEDs, which in my opinion are some of the better products, I came across these which were really keenly priced. But this one specifically has a DMX controller built in, or decoder rather, so you only apply 24 volts and a DMX signal, and supposedly it should drive the LEDs properly. So one of the things that I was looking at is, although you can quite easily buy RGB modules, you then have to design the DC to DC converter to drive them, and then the whole project starts getting really expensive. So the fact that this has everything built in, and they were coming out at just over £3 each, I was quite interested and had a chat with the guy, and yeah, ended up with 59 of them. Right, so just looking at these a bit closer, these are 30 centimetres each, or around 12 inches, and the idea is that they slot together to form a nice long linear bar, which will allow you to illuminate a wall, so wall washing. These are fitted with the oval optics, so you can pick different lenses when you order them, 6 degree, 15 degree, 25 degree spot, or the oval, which is 8 by 25, and what that does is it gives if you have it up against the wall like this, it gives a nice wide spread of light across the wall, giving really good colour mixing, but the beam in this plane is quite narrow, so when you've got it aimed at the wall, you're not wasting light on the floor or focusing too much light up close against the light. It sort of gives a nice spread all the way down the wall. And each module comes with an interconnecting cable, so it's got a Microfit Junior connector, which is nice. I've got lots of these connectors, so I can make up my own cable looms without needing to source them, because actually if you try and buy these, they're really expensive to have them from RS. And it looks like the top just comes off, so I managed to pull this one away, and this gives access to the two Molex connectors, which allows you to electrically link each of the bars together. Right, so what we've got is the 9 LEDs on the front, so we've got 3 red, 3 green and 3 blue, and behind these lenses are Luxian Rebel LEDs. So these are a little bit old technology compared to some of the newer LEDs, but things haven't changed that much. So the luminous efficiency is pretty much the same and has been for 5 or 6 years now. What the manufacturers have been working on is increasing the flux density. So these Luxian Rebel LEDs are pretty small, but the new LEDs like the Luxian Z are much smaller in their package, so you can pack them tighter together to create a higher flux density, for a given footprint. But obviously, you've got all the thermal considerations to go around trying to get that much heat out of a small PCB. And then what we've got here, just starting on the right-hand side, is we've got a connection to the shield. Curiously, it hasn't got a bolt or anything holding the PCB to this shield post, but this is capacitively coupled and then through a 100 ohm resistor to chassis ground. So that's just to provide some EMC shielding of any of the switching frequency that might be transferred into the aluminium package on this device. And then what we've got is the two connectors here for the 24 volts input and the 24 volts output, and the DMX input and the DMX output. So this just allows you to link the devices together. And then if we zoom in a little bit closer on sort of the business end of the PCB, what we've got here is an RS485 transceiver. So this is the ADM 483 from analog devices, but it's pretty much the same as the Max 485 and a couple of others. So what this is doing is just translating the differential signal from the Molex connector for the DMX and connecting it up to the microcontroller at sort of 5 volts single-ended. Curiously, there are 2 of these 485 transceivers. This one appears to be connected to this input connector, and this one appears to go off to the output connector. So I'm not sure whether it's just directly repeating and buffering the RS485, or whether we'll have to test shortly, but I don't know whether it's you've got your RS485 coming in here to the transceiver, going through to the microcontroller, and then back out to this one. So I don't know if it's doing the shifting of DMX addresses or whether it's purely just buffering the signal. And then just down here we've got a LM7805, so a 5 volt regulator, just a linear regulator, which is powered directly from the 24 volt supply. And that's fine. There's not a lot going on this PCB in terms of 5 volt current draw. Plus this is still heat sinked onto this big heat sink on the back. So yeah, this 5 volts just supplying these 2 transceivers and the microcontroller. And then what we've got here, if we look a little bit closer, is we've got a microcontroller here, which is sort of the brains of the outfit. We've got a switch here, which I'm assuming is used to set something to do with the DMX addressing. We'll have to find out. I was just having a quick scout around on the internet. It looks like Dial-Lite Luma drives went into liquidation last year, which explains why I didn't get a response about the datasheet request. So we're going to have to do a bit of faffing around and trying to work out how this works. Hopefully we won't brick the device by fiddling with this button. We'll see how it all behaves. But this microcontroller here isn't branded in terms of microchip part or anything like that. It has the markings Eldo LED on it. So Eldo LED is a company which I've just found on the internet, which creates LED drivers, and so Eldo LED up here. And this product looks fairly similar in terms of sort of application. So it's got a constant current LED driver. It does say from one high precision current source, and then it's configurable, whether you want DALI or DMX control, and then it just has the RGB outputs from here. So I don't know whether it's a custom ASIC or whether it's just a microcontroller with an analog front end for controlling the LEDs, but I haven't been able to find really much about this chip. And then just lurking in the background here, we've got an 8 megahertz crystal, which is pretty standard for DMX type applications. It happens to divide down nicely for the DMX baud rate. And then finally what we've got is a single DC to DC chip. So I mentioned that product on the datasheet said it had one high precision current source. And what we've got here is the ST, what is it? The L5973D, which is a buck regulator, a single channel, has input voltage from 4 to 36 volts. Obviously that's within the range of the 24 volts that we're feeding it. And then a single voltage output anywhere between sort of 1.25 and 35 volts. So what I'm assuming that they're doing, because that's the only DC to DC on the board, so you've got your inductor here, there's a flyback diode just hiding in here, the capacitor which is just smoothing the switch signal, but yeah, just the one DC to DC chip. So what I'm assuming that they're doing is maybe outputting a known constant voltage higher than the forward voltage of the 3 LEDs in series. So the blue and the green tend to have the highest forward voltage. So 3 LEDs, maybe 4 volts forward voltage is getting on for 12 volts. So maybe they're regulating down to around 12 volts with a little bit of headroom, and then there's not much in terms of, there's no op amps or anything like that up here. There's a couple of transistors, so one transistor which appears to be for each channel. But I can't really see much in the way of like current sensing resistors or anything like that. There obviously is some feedback going on because there's quite a few packs of resistors and a few R's and C's dotted around the place. But what I imagine they're doing is setting this voltage up to let's say 15 volts or something like that, so there's a bit of headroom, and then applying a known PWM waveform to each of these LEDs. So for example, let's say this is regulating it to 15 volts, and let's say the LEDs in the red channel had a forward voltage of 7.5 volts at full brightness, then you'd know that you could scale up to 50% duty cycle to get full brightness on the red channel, and if you went over that you'd be overdriving the LEDs, and then maybe like for 100% brightness or 350 milliamps or whatever that we're driving the green and blues at, you know, the max duty cycle would be 70%, and if you went over that you'd be overdriving it, but you'd linearly scale the brightness between 0 and 70%. So I'm assuming they're doing some kind of thing like that. I don't think they're monitoring the current from what I can see through each of the channels, because unless there's some really big drop of resistors, which I haven't come across yet, you would need some op amps to amplify up the signal to make it suitable for reading on a micro, unless it has it built in. So we might have to do a little bit of probing. But yeah, there's not really much on the board, so that's quite simple in comparison to sort of the LED driver that I would have designed to drive one of these linear arrays. So that's quite a neat solution. So I think what we'll do now is we'll have a look at powering up the device and see if we can gain a little bit of insight as to what's going on. Okay, so I've just made up a cable to connect into here. So I've got a Molex microfit here with the 24 volts on the red and black, and then the DMX on the other three pins. Rather than splicing into the 0 volts for the 0 volt return for the DMX, I've just used that other pin that was connected with 100 ohms to the chassis ground. So the arrangement that we had, oops, just bang the camera. The arrangement that we had was you had the chassis, which I'll draw like this, with a capacitor to AC couple the chassis, and then we had 100 ohms, and then that went to the circuit 0 volts. So that pin is presented just here, so it's just got an impedance of 100 ohms. So that will be fine for the DMX. We're not putting really any current through the DMX, so there'll be hardly any voltage drop here. And just for testing, that'll be fine rather than splicing in on the wiring. So at the moment the DMX is not connected. I've just got bare ends on there, but I have got 24 volts connected. So let's see what happens if we plug this in. Okay, so with no DMX signal, you saw it just ramped up to full brightness, and they are, wow, really quite bright. It's drawing close to 500 milliamps from the 24 volt rail, and that gives quite good colour mixing. Just that's about 60 millimeters up from the desk, and already there's not really any hot spots of colour. It obviously isn't colour corrected at the moment, so we're not getting a pure white. There's a bit more blue and red from what I can see, so it would need the gamma correction, but yeah, so that seems to work. Now my theory on the DC to DC was that this would just be some pre-regulated voltage just higher than you know, the highest voltage of the series string of LEDs. And I'm assuming that the LEDs are connected up in series string, so a series string of blue, series string of green, and a series string of red. So let's see what voltage we're actually getting from the DC to DC converter. Right, so we've got the input voltage set precisely at 24 volts. So let's make a measurement of the output from the DC to DC. So we've got chassis ground just here. It's a little bit bright, so I'm having trouble seeing. Okay, and then we should have the DC to DC output on this capacitor here. And that's about 19.1 volts, which is quite high actually. Maybe I'm wrong in what they're doing with this. No, it doesn't make sense. Let me try turning down the voltage and see if this voltage remains stable. Right, so we're down at 21 volts now. I don't think I saw any change in the brightness. And that's still the same voltage. So at the moment we've got a fixed voltage coming out the DC to DC. And then I mean, that's quite a high voltage. I'm not quite sure I'll have to verify the operation, but they must be PWMing these LEDs to maintain a constant current, either based on some lookup table that says, you know, at 350 milliamps we're going to see 12 volts across these LEDs, so we need to adjust the duty cycle so you see 12 volts. That's all I can think of at the moment. Right, so I've connected up the DMX interface. This is the same DMX interface I used on the Disco Lights video. So it's just a Raspberry Pi with a BitWizard PCB on top, which is a DMX interface PCB that someone manufactured on the internet. And then this connects to the PC via USB, and I'm just running a program called QLight Controller Plus, which is a PC-based DMX control desk. And all of the intensity settings are at 0 now, so all of the LEDs have turned off. So what might be interesting is to take a look at what voltage we're getting from the DC to DC converter now. So if I stick this on here, you can see it's reading about 3.5 volts. So that DC to DC converter is actively being controlled in some way. So if we turn up the red LEDs, that's at full brightness, and that goes up to around 7 volts. What about the green channel? It's about 6 volts as well. And the blue channel is about 7 volts. So that's not making a huge deal of sense to me. If I turn on the blue and the green, presumably it will be sort of the 6 and the 7 together, so somewhere around 13 volts. And then if I add the red in, that's the remaining 6 volts. Yeah, that doesn't quite make sense. Yeah, so I'm a little bit stuck at the moment in trying to work out how this works, because what I was assuming was that there are series strings of LEDs, but when these are at full power, you know, like the blue string is going to be around 10.5 volts, so is the green, and the red will be somewhere around 7.5 volts. And what I was envisaging is that you would pre-regulate the 24 volts to something close to, you know, the maximum voltage that we're going to see of the series string of LEDs, plus a bit of headroom, and then just maybe PWM the LEDs to get the desired current through them, or average current through them. But what we're seeing is some voltages that don't really make sense to me, and unfortunately the LEDs are obscured by the lenses, so I can't even get in to see exactly where the traces for the LEDs go, and you can see quite a few traces disappearing under each of these LED lenses. So I'm a little bit puzzled. I can't quite work out how they're doing the current control with a single constant current driver, or with a single constant voltage driver, because the other way that you could potentially do it if your DC to DC converter had a fast enough recovery time would be you put all of the colours in series and have a transistor switching across the LEDs and shorting them out, but you need really fast response time. You know, you wouldn't want any capacitors, because if you're PWMing these LEDs, you know, when they turn off, you're going to suddenly dump all the voltage across these LEDs instead. So that doesn't really work. I just can't in my head work out quite how they're controlling this. So I'm probably going to leave that there in terms of you know, how the circuit's working. If anyone has any bright ideas, please leave it in the comments below, because I'm really a little bit puzzled by this. But one other thing I wanted to do is work out how this DMX addressing and everything actually worked, because I mentioned there's two RS485 transceivers, and it is labelled in and out, so it suggests there is some direction. So I've got another one of the modules with the cable attached, so we can attach that to here. Right, so let's try turning up the faders. So we'll try channel 1. Okay, so that's just the reds on the first PCB. That's how it was before. So either these PCBs aren't connected up properly, or they're all individually addressed. So channel 4, and then I guess channel 7. So channel 8 should be this top PCB. Yeah, so we've got full full individual control of each set of PCBs. So this microcontroller is shifting the DMX addressing because you know, there's no dip switches, and I haven't set these to different DMX addresses. So it's translating sort of channel 4 back down to channel 1 for this PCB, and you know, as it goes down the line, it must be doing the same thing. So I guess the final question is what this button does and whether it's some way of addressing the PCBs. If you press the buttons, it doesn't seem to do anything. Just as it is now, it's all still behaving the same. Let's unplug the DMX interface. And we'll turn on power again. Maybe push the button. Oh, so it's just a self-test function. So if I push the button, they all come on. Push it again, nothing. Oh, and it's going through a cycle. So yeah, it's got some self-testing built in. That's nothing to do with the DMX control. Okay, so that's probably it for this video. As I said, if you have any ideas on how the constant current driver might be working, leave it below in the comments. I would be interested. I'm going to have a think about it and see if I can work out what's going on, but at the moment it's stumped me a little bit. But anyway, until next time, thanks for watching.